I feel like the rest of it is stuff.
Bitch. So see.
The Declaration of Independence was a lie.
Hello.
It's
Welcome
right.
to the final GR lecture. I will be your professor. That's
Right, guys.
Carlton
Crazy.
Dr. Alejandro Fluoride. That's me. We're going to be talking about really big things, really small things, and the paths that they take all the way out.
All the way to the edge of the whiteboard. Are you coming to the deputy?
Papa squat. Alright.
It said you're gonna have to check. If you want accommodations,
Okay, we're gonna get started. Alright, so it's been very satisfying to watch you all work on the final. I know it's challenging, but not satisfying in like a sadistic sense. I don't mean that, but I feel like, I hope you're learning. I mean, a final is like, to me a final is not like a test of what you know, it's can you take the things you've learned and kind of use them, you know? That's why I like to do it out of class, so that you actually have time to assimilate the ideas and maybe work something that you haven't seen before, but hopefully utilizing and appreciating the tools that you've developed. So I've been impressed with what I've seen. I might extend my help hours tomorrow past 5 if people are still around and still need help. So if you can't make it between 2 and 5 tomorrow, come at the end, and if people still need help, I'll hang around. All right. Okay. So we are going to talk this week about another application of Einstein's equations, which this is sort of the theme of this course. Like, you know, if it were up to me, general relativity would be a 3-semester course, right? I would give you all the foundation stuff, and then we would have a whole semester of basically studying black holes and all the wonderful things about black holes and spherical geometries, and then we would have a whole semester on cosmology. When I was a CU grad student, I took an entire semester on the subject I'm going to try and teach you in 2 days. So clearly I'm going to throw a lot at you really fast, and I'm not expecting it to stick. A lot of nomenclature, words, ideas. I'm going to try and get you to some of the key things that you know happen in cosmology. So today we'll see at least 2 things. We will see the expansion of the universe and the Big Bang today. And then next time we'll see a lot of cosmological problems that you've probably heard of and their solution through a mechanism called inflation. Okay, but I'm going to try and sort of mix today a lot of concept and concrete application of general relativity, because that's what the course is about. So this is going to be our Cosmology 1, and the theme of today is what are generically called Friedmann, Robertson-Walker cosmologies. Okay. So when we've tried to piece together solutions to Einstein's equations before, clearly one of the principles that has guided us, because they're generically a very nasty set of coupled partial differential equations. So we've used the tool of symmetry to reduce a lot of that work, and the same thing is going to apply when we try and apply this to cosmology. And the sort of starting point for cosmology, which is actually a little bit funny, like cosmology people think of, what's the study of the entire universe? Like, that's everything. That's the biggest system you could possibly study. You know, the Physics 1 students love cosmology. A system equals everything. I've never seen a Physics 1 student actually do cosmology, but anyway. But if you think about it, like, you're basically just taking your system to be everything. And ostensibly, like, that should be the hardest problem in all of physics, right? But we clearly don't do that. So when we do cosmology, what we do to make it tractable, Mike, what are you doing?
What?
Just behave. You're reminding me of a TV character right now for some reason. It's funny, like I feel like I'm number one in the videos of the class, and then Mike's number 2 and Leo's number 3.
Right, Leo's.
Has anyone actually commented on Leo?
Leo's. I don't know if people have commented. They should.
Have they
And
seen Leo?
I don't want to talk about it. These videos are not for the audience. They're for you. They're not for them. They're lucky they're happening. Well, I don't know. Maybe they're unlucky they're happening. I don't know. Anyway, I don't want to this is getting meta. We got to somehow make this tractable. Like, we can't take every atom in the universe individually into account. So what do? We smooth over. We are basically going to treat the entire universe like soup. Okay? We're not even going to think about structure at the level of galaxies. We're just going to think of everything as a continuous soup of stuff. Okay? And ask the really, really big questions. Because truthfully, if you look at length scales for the entire universe, on that length scale, you don't actually resolve even galaxies. It's just this huge soup. Okay? It's basically continuous. So that's the way that you initially apply general relativity to describe the entire universe. Now, of course, there is a very, very important and extraordinarily challenging intermediate problem, which is to say, okay, how do you explain structure formation? How do you explain the fact that there are galaxies and it's not just this continuous distribution? And that, of course, involves general relativity, but it also includes a lot more. Okay? So we're going to do this. Thanks, I was hungry. You set up on the counter. And you too. Oh, you brought me 3. That's the perfect number. Anyway, so we're going to treat the universe like a soup. We're still going to get to a lot of amazing results. And of course, all of this is the backbone for doing even more refined treatments. Okay? So let's see. All right, so a couple of important things that we should expect going into applying general relativity to the entire universe. First of all, we should expect that we are not doing a vacuum solution to Einstein's equations. When we did the Schwarzschild geometry, we just said, I'm going to be outside of the planet or star. So in that case, we could set T nu equals to 0, and that kind of simplified Einstein's equation. We can't be outside of the universe. We're in the universe, and there's stuff in the universe. So we are going to have to contend with Einstein's equations for the non-zero T nu. Additionally, and this is counter to what Einstein was originally motivated to do, but we are in the modern era, we cannot assume time independence because we know that the universe is evolving with time. So there's no safe assumption that the universe is static. Einstein really wanted the universe to be static. That's in fact why he introduced the cosmological constant in the first place, and you can imagine how disappointed he was when it was discovered that the universe is in fact not static. And then to actually get somewhere with Einstein's otherwise unworldly difficult equations, we're going to have to identify symmetries that are present. And in choosing or identifying symmetries, that's also going to motivate the choice of coordinates that we're going to use. It's the same thing we did with the Schwarzschild geometry, where we said we're going to assume spherical symmetry, and therefore starting with something like spherical polar coordinates is probably a good way to go with that geometry. All right. So let's start with the symmetries of space-time in the cosmological context. So we have 2 observed symmetries of the spatial geometry of our universe. Now, I'm going to be very careful in this lecture in distinguishing between spatial and space-time. The difference is obvious. Space-time includes space and time. When I refer to spatial, I only mean the spatial part of the geometry. And I'm going to make that distinction persistently throughout the lecture. So right now, I'm only talking about spatial symmetries. But when we look out in the universe, we generically geometry and spatial isotropy. So the idea of spatial homogeneity is basically rooted in translational invariance. That is, if I'm here and I say, this is what the geometry looks like, and then I go over here and I say, what does the geometry look like? And I say, oh, it looks the same as it does over here. That's homogeneity. Okay? Isotropy is, of course, rotational invariance. If I look over there, I see the same thing as I do if I look over there. Now, these kind of sound like the same thing. Like over there looks the same as over there. But they're not actually necessarily the same thing. Let me give you an example. I'm going to give you a space which is homogeneous, but is not isotropic. You ready? So an infinite cylinder is homogeneous. You can move anywhere on the surface of that cylinder and it looks the same. But if you look in this direction, you're looking in a direction which winds around. And if you look that way, you're looking in an infinite direction. So things look the same from one point to another, but the direction you look in changes what you see. Now, can anybody give me an example of a space which is isotropic but not homogeneous?
Serial.
Serial.
It's not homogeneous, right? But it still has some rotational invariance, right?
You're rotating. You're trying to earn your reputation on YouTube. I'm going to try and make cereal. Okay. Suppose I gave you a lot of cereal. Like an amount of cereal equal to 1 trillion times the mass of the sun.
That's a lot of cereal.
What would that cereal become? A black hole. Yeah, a spherically symmetric geometry, like a Schwarzschild geometry, if you're at the center of the geometry and you look in all directions, it looks the same. That's the point of spherical symmetry. Right? If you look off over here, it looks the same as if you look off over there. But it's not homogeneous, because if I'm here, I can say, okay, I'm this far from the center, but if I'm here, I have a different experience because I'm closer to the center. So a spherically symmetric geometry like the Schwarzschild is isotropic about the center of the geometry, but it's certainly not homogeneous. Okay. So do you appreciate the difference between these two things? Now here's the key. If you put them together, they make a very profound statement, because homogeneity means I can go anywhere in the space-time, and in any direction I look, everything looks the same. This means that there can be no center to our universe.
Or that everything is the center of the universe.
Or that everything is democratically on the same footing as everything else. Okay? Our universe. Now, I want you to think about this, because a lot of people come into a discussion of cosmology with this basic idea that the universe exploded from a point, and then there's this idea, well, that point is the center of the universe. There is no center to our universe. Every point in our space is as good as every other point in our space. You'd see the same thing no matter where you are. Okay? So, together, so if we add these two together, then what it actually tells us is that we have a maximally symmetric spatial geometry. And we have that's actually a technical word, maximally symmetric. We've seen it before. We've seen it for space-time geometries, that maximally symmetric geometries have the highest degree of symmetry you could ask for. And they actually have a simplification when you're looking for the curvature tensor, which we're going to use in a few minutes. So this is a very powerful observation. Yeah?
Does that nowhere is like the center, does that require some sort of like periodic 4D boundary? Like,
No.
How's that
No. It's just the way our geometry is. Let me give you an example. I'll give you an example of a geometry which satisfies this, okay? The surface of that sphere. It's homogeneous and it's isotropic.
Yeah, and then it has periodic boundary conditions, right?
No. You're only on the surface. The interior doesn't exist.
Yeah, but I mean, the surface has periodic boundary conditions.
But you don't have to have this. I mean, infinite flat space is the same way.
It's just hard to imagine that.
Well, infinite flat space is the same. it's going to turn out that there are three geometries that we're going to contend with. This will be one, flat space will be another, and then there'll be a third. But the flat space is the same. There's no boundaries. It's homogeneous and it's isotropic. Like the plane R2, it's homogeneous. You can move anywhere you want. Still looks the same, and it's isotropic.
So does that require that the universe is like infinite?
It depends. No. Whether the universe is infinite or not it's a separate question. If it's, I'll get to that. But it turns out we haven't yet said what the shape of the universe is. It could be a sphere. It could be something else. In some cases, it implies that the universe is finite. In some cases, it could be infinite. Or you could actually have the universe be topologically non-trivial. So what I mean by that is I could say that the universe is spatially flat. And then you might say, oh, well, that's the plane, and the plane is infinite. Well, not necessarily, because I can take the plane and form a cylinder. And it's still flat, but it's finite. That's an additional freedom. That's specifying the topology of the universe, which is not what we're going to get into today. Because a large part of our understanding of the universe is based on the observable universe. And there's a way you can define that, and there's parts of the universe that are simply not observable. And to know whether the universe is infinite or not, you have to know about the entire universe, not just the observable universe. So a lot of these considerations are going to you can ask these questions in an even more informed way as we get through the content of today and Thursday's lectures. So keep chewing on those, and I might be able to give you better answers later. Okay, so these are the symmetries we're going to exploit. And the second thing we're going to do is we're going to make use of these symmetries to consider a coordinate choice. And the convention in cosmology is to adopt what are called comoving coordinates. Comoving spatial coordinates. So let me just give you a quick picture of what comoving spatial coordinates mean. So let's suppose that I have a planet here and I have a planet here, and the coordinate distance between them as measured, along some axis, say the x-axis, is delta x. Okay, that's the coordinate distance. To get the actual physical distance, you have to take the coordinate distance and combine it with the metric. That's the function of the metric. That's how you say the metric defines space-time distances. You take the metric, the coordinate differences, and then you get a physical distance. Okay? Now let's suppose that because of the behavior of the universe, these two things are moving apart. So I'm kind of skipping ahead, but let me just say this. The universe is expanding. So these two things are actually moving apart due to the expansion of the universe. I'm not talking about these things are in orbit and right at this moment they happen to be moving in opposite directions. I'm talking about two things which are just sitting still, and because the universe is growing, they're gently moving apart. Okay? That's the kind of motion I'm talking about. We're going to use coordinates such that even though these two things are moving further apart, their coordinate distance will be fixed. These are called comoving coordinates. So you can think that the x-axis is expanding with the expansion of the universe. Or contracting if we're looking at a scenario where it happens to contract. So does that idea of comoving coordinates make sense? You're basically letting the coordinates expand or contract with the geometry if it happens to be doing one of those. Of course, if the geometry is static, those coordinates don't do anything. Okay, with that in mind, we now get into the mathy math stuff. So if we put all this together, then we can do what we normally do, which is before we even talk about Einstein's equations, we can write down a fiducial form of the metric. We don't have to write down this completely unknown symmetric 4x4 tensor, or this tensor which can be represented by a symmetric 4x4 matrix. We can actually write down something which is a little more refined, and the form of that is going to be the following. And of course, eventually in all of this, we have to employ Einstein's equations. Okay? Now, this guy is a dimension-full quantity. So that just means it literally has dimensions of length squared, okay? This is dimension-full. It has dimensions of length squared because there's secretly a c-squared factor sitting in front of that, okay? This is length squared. So this quantity right here is therefore dimensionless, okay? So this guy carries no actual length dimensions. It can talk about the shape of things. So it's kind of like unit vectors, right? Unit vectors don't actually tell you about length, or they're normalized to a unit length. They tell you more about direction than they tell you about distance. You actually have to multiply the unit vectors by components. Okay, this quantity you might notice is time independent. There's no time in there because it depends on u and it involves the du, I, du, j coordinate differentials, but those are the spatial coordinates. And this is the time independent spatial geometry. Okay, which we often call d sigma squared. And you know, I thought about kind of streamlining this lecture and just kind of cutting out a lot of the jargon and the notation. But truthfully, like, if any of you are interested in this at all, you're going to eventually look at cosmology books or take a cosmology class or read articles or whatever. So I think exposing you to the standard notation, for as much of a headache as it is, it's going to be of a benefit. So when I say d sigma squared, I'm just talking about this spatial part of the metric. Okay? All right. So the essential idea of this form of the metric is that this is the geometry as described in a coordinate system that is adapted to an observer who is at rest with the overall universe. Now what do I mean by that? Well, the universe is going to have this energy momentum stuff. It's the source. And when we studied energy momentum tensors, we talked about, for example, if you think of a perfect fluid, you can ask yourself, am I at rest with respect to the perfect fluid, or am I moving relative to the perfect fluid? All right. Well, so you can ask yourself, if the universe is this fluid, am I moving with respect to the universe or not? We're going to carry this analysis out in the simplest case, which is where you are at rest with respect to the overall fluid of the universe. On Earth, our observations are not that. The Earth is moving. Okay? And so it's interesting because, and I don't know if any of you have noticed this, like we often say that the universe is homogeneous and isotropic, so everything should look the same. Well, that's not true if you're actually moving through the universe. Because if you're moving through the universe, then your motion creates a special direction because stuff is coming at you, stuff is moving away from you. And in fact, if you look at a picture, have any of you ever seen a picture of the CMB, the cosmic microwave background radiation? Have you seen it without the removal of the dipole effect from the motion of the Earth? So if you look at a CMB picture, sometimes it'll be uniform. And that's kind of removing the motion of the Earth from what you see. But a lot of times they'll just show you the raw data. What does the CMB look like from the Earth? And when you look at it from the Earth, it's got this sort of dipole pattern, these sort of yellowish areas. And that's because the Earth is doing that. It's moving. And so there's stuff in the CMB coming at us, and there's stuff in the CMB moving away from us. Okay? We're not going to do our analysis based on what we see from the Earth. That's just hard. We're just going to assume we're at rest with respect to the universe. And then you can always go back and transform to the frame of the Earth if you really, really, really want to. Okay. So, maximally symmetric is super useful because, as we learned when we talked about maximally symmetric spaces, it tells us something about the form of the curvature tensor. Okay? Now this is one of those places where it's going to be a little painful, but bear with me. It's only the spatial part that is maximally symmetric. So when I talk about the curvature of the spatial part, I'm only going to use the spatial indices. I'm not going to include time. So I'm not going to use Greek indices. Greek indices, mu, nu, rho, sigma, those go over all 4 dimensions. Okay. When I use I, j, k, those only run over 1, 2, 3, the spatial dimensions. But otherwise, my formulas look exactly the same. So we had a formula that said, if you have a maximally symmetric geometry, then the curvature tensor takes this form. Okay, it looks a little weird, but when we saw this before, this was r, mu, nu, rho, sigma. This was a constant, and then these were all the g metrics. G, mu, nu, g, rho, sigma, blah, 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 blah. So in a maximally symmetric space, we get this incredibly powerful result that if I give you the metric, you can algebraically calculate the curvature tensor. You don't have to take any derivatives of the metric. You don't have to form Christoffel symbols. You don't have to do all that crap. You just literally multiply the metric together in this combination. Okay? Now, in Einstein's equations, we don't use the curvature tensor directly. Rather, we use the Ricci tensor. That's the 2-index contraction of this thing. So it's this with only 2 indices. So if we do the contraction to get the Ricci tensor, that we achieve by taking a metric. Let's see if I can do this. Yeah. Okay. So we use a factor of the inverse metric to raise the 3rd index and make it an I, and then that I sums with that I and leaves me with a J and an L. So that's the definition of the Ricci tensor in terms of the curvature tensor. Okay. But if you literally plug in this formula for the curvature tensor, all you're doing is you're taking inverse metrics and you're combining them with various metrics. So that simplifies, and this ends up just giving you 2k times the metric. So for maximally symmetric geometry, the spatial curvature tensor is super clean. Man, you guys, so many of you are on your phones. This physics want to be cracking skulls. You guys are breaking my heart. For a maximally symmetric space, the curvature tensor is a very nice form, but the Ricci tensor is super nice. It's just proportional to the metric. And in fact, you can take it one more step and say the Ricci scalar, which also appears in Einstein's equation. The Ricci scalar we get by contracting the Ricci tensor's indices. So this just raises the J, turns it into an L, and then the L is summed over. This just becomes 6 times K. Okay. So what does this mean? Well, it's actually something we could have expected. If a space is homogeneous and isotropic, the fact that it's homogeneous means if I know the curvature at one point, if I move to another point, the curvature has to be exactly the same. If the curvature was different from one point to another, it wouldn't be a homogeneous space. Okay? But if the curvature is the same at every point in space, then what kind of function of spatial coordinates should the curvature be? Say again? It should be a constant. Okay? So what we're finding is that the curvature is really determined by one number, k. Just one number. Yeah.
Is this k in 6k the same as the index k?
No, sorry. This is just a constant. It's not a label. I know. Apologies for that. And again, I would have picked a different letter, but this is the standard notation in the literature. So yeah, k is just right now a constant. Okay, and then what we can do is really look at the possible geometries by different cases of k. All right, so k is just a number, so really all we should care about is whether k is 0, positive, or negative. Okay. If k is 0, then our spatial geometry, that is just this part of the metric, If k is 0, our spatial geometry is flat.
Isn't it flat, flat? Because,
It's flat, flat. Yeah, it's flat, flat. And we know what flat looks like, and this is unfortunate, but just going to do it. Okay, so a three-dimensional geometry, which is flat, flat, we can express with a metric of this form, where this is kind of like, it's spherical polar coordinates. Instead of calling it r, I'm calling it chi. You'll understand why in a minute. But chi is basically the radial coordinate, and this is r squared d omega squared, where that d omega is the standard d omega. So it's d theta squared plus sine squared theta d phi squared. Yeah.
is there any particular reason we're picking spherical coordinates as opposed to Cartesian?
Yes.
Okay.
Yes. Okay, because the next two examples are going to make use of that same coordinate choice, but with non-trivial geometries. So when kappa is greater than 0, we have a positively curved space. Oh, sorry, go ahead.
Sorry, why is there a subscript on the omega?
Well, I mean, it doesn't have to be there as long as you understand that that's the d omega of 2 angular dimensions.
Okay.
I have worked on problems in my career where I was working on like a 6-sphere. So I needed to write that so that no one got confused and thought I was just talking about d theta squared plus sine squared. So maybe I don't need that as long as you're all comfortable that that's the normal two-dimensional theta phi solid angle. Okay, when k is bigger than 0, we have a positive curvature in our geometry. And in that case, we have a similar form. But in these coordinates, and this is where it would look very different if we used Cartesian coordinates, instead of chi multiplying the angular part as chi squared, we actually have a sine squared of chi. Okay? This is the metric of a 3-sphere. So over here, we have, for k equals 0, we literally have R3. If k is positive, then that metric describes a 3-sphere. And if you're wondering, Bree, that is secretly the definition of d omega 3 squared. Okay. And then lastly, if kappa, or k, I think it's going to switch to kappa later, that's why I'm getting ahead of myself. Then this becomes a hyperbolic sign. And in this case, we're dealing with a hyperbolic spatial geometry. Okay. And for anyone who attended my public lecture, I talked a lot about the hyperbolic geometry. Drew those Poincare disks, drew a 2-dimensional hyperbolic geometry. This is 3-dimensional. But we have special words that we attach to these. Of course, R3 is just flat. For the spherical case, we call that a closed spatial geometry, and for the hyperbolic case, we call it an open spatial geometry. It's just words that you'll hear or see in the literature of cosmology. So people will talk about is the universe closed, open, or flat? They're just referring to what is the spatial geometry. And again, this is just spatial. I'm not talking about space-time yet. Okay. Notice I haven't even touched Einstein's equation yet, and we will get to that. So what we're going to do, this notation is fine, but it really means if you're trying to work with this case and then you want to switch to this case, your expressions really change a lot because you've got to switch from just having chi squared to a function of chi, and then a different function if it's so what we're going to do is we're going to rewrite this with a different set of coordinates so that switching from one case to another is a more trivial step. It's a smaller tweak than actually replacing the various functions here. And so to that end, we're going to introduce a new coordinate using the following definition. Okay, that is an implicit definition of a new coordinate I'm going to call r bar. All right. And you can think of it like a new radial coordinate. And in terms of this radial coordinate, d sigma squared is just going to become dr bar squared over 1 minus k r bar squared plus r bar squared d omega squared, where k takes the values 0 or plus or minus 1. Okay? So let me just very quickly connect this back to, I mean, that kind of looks like magic, but let me very quickly connect it back to here. So let's take the case when k is equal to minus 1. If k is equal to minus 1 and I look at this definition, then this is of course telling me that d chi is just dr bar over the square root of 1 plus r bar squared. I just set k equals to minus 1 there. Okay? And then if you take this expression and you actually solve for what does chi look like as a function of r bar, it's just the inverse sinh of r bar, which you can see is going to reproduce the sinh function that came into the metric when you're using the chi coordinate. And then similarly, if you plug in k equals 0, then d chi just becomes dr bar. And if you plug in k equals plus 1, then you get a different expression, and when you solve it, you'll get an inverse sign. Okay. Now let's go back and do one more check. Let's do the k equals 0 case. If I set k equals to 0, then in this formula, k equals 0 means that d chi is dr bar, and this becomes d sigma squared is d chi squared plus chi squared d omega squared, which is exactly what we have here. So this compact expression is giving us all of these three possible cases, but the only thing we have to do is change that letter k from 1 to 0 to minus 1. We don't have to work with, am I doing chi squared or sine squared or sinh squared? Okay? Okay. So if we go back to this guy up here, and we use our definitions, then this guy is now going to take the following form, dt minus dt squared plus, we still have that r factor right there. And then we've got our nice expression in terms of this dr bar. Okay. And this is what is generically called a Robertson-Walker. Can't spell Robertson today. Robertson-Walker metric. So this is the form of the metric you would anticipate from spatial homogeneity, spatial isotropy, but allowing time dependence. Okay, and these names are going to pop up a couple of times. They're very prominent in the early applications of GR to cosmology. And it's funny, I had a my last senior design student, he was a senior design student, he was a grad student. He ended up doing a very GR intensive master's thesis. This is Zach Polanski, for those of you who might have met him. But it's like every single day we had a meeting. Like once a week we'd have a meeting. Every meeting we had, he'd be like, "Oh, I got a new set of coordinates." He literally changed coordinates for every meeting. It got annoying. That's exactly what I'm going to do to you today. I'm just going to keep changing coordinates. So suck it up. All right, so we can actually make this look even nicer with a change of coordinates. And so getting rid of this garbage, which I'm probably going to desperately need later on, but I got to write somewhere. So now what I'm going to do is I'm going to define a quantity called A of t, which is r of t over the current length scale, r naught. This is, of course, now a dimensionless scale factor. Okay? It's dimensionless because I take a dimension full quantity and I divide it by a dimension full quantity. Like if you literally put these quantities in units, there would be no units left. So it's dimensionless. Okay? We got to get something to have dimensions, so we can now define a dimension full, and I guess these are definitions. We can define a dimension full radial coordinate by taking some fiducial scale r naught. This r naught is just some fixed length. Okay? It's just a constant. It doesn't matter what its value is. If I divide this by this, it gets rid of the dimensions. And similarly, if I take the dimensionless coordinate r and I just multiply it by this constant thing with units of meters, if you're putting in units, then this has units. So this is now a dimension full radial coordinate. And then lastly, we're going to define a dimension full curvature. With the confusing capital K. Because this is clearly not that. This is like disconnected, looks more like a Chinese character. Capital K versus little k. We're just going to use capital K going forward, so it shouldn't get confusing. All right? And then, with all of that in play, our metric now takes the following form. Okay? I mean, notice you can see this immediately. If r bar squared is getting replaced by r, that means that r bar is getting replaced by little r over big R naught. And then that's just going to cancel the r naught squared there. And then plus r squared d omega squared. Okay. So, looking at this for a moment, if you think about this metric, yeah, go ahead.
I'm worried that this is going to be like the exact repeat of what the question I asked a couple weeks ago, but how can you just switch r bar squared to just r squared?
I didn't. I switched r bar to r, but I also switched little k to big K.
But what about right before the d omega?
But this is combined with that. You got to make the replacement everywhere. So this got replaced by a squared. Similarly, the same thing with this r and this r bar there. Okay, so it all works out. Is that good? What the hell was I about to say? Maybe it's like going for a loop. Oh man, I accidentally printed my notes on. Oh yeah, no, I was about to say. Okay, so this metric has how many unknowns in it? How many unknowns are in this metric? Two. What are they? A of t and k. K is a constant, and then A of t is just some function of time. So if you think about it, Einstein's equations really only have to tell us what those two unknowns are. So instead of having 16, well, it's not 16 because it's symmetric, but 10 components of the metric, which could be functions of all the different coordinates, we've reduced all the unknowns down to two. One's a constant and one's a function of only time. So when we turn never print my notes on both sides. So when we turn to Einstein's equations, this is going to help dramatically simplify things. Okay, so we're going to go into Einstein's equations now. And in doing so, remember, we have to utilize a non-zero energy momentum tensor. The universe is full of stuff, and that stuff is influencing the behavior of the universe. Well, you might wonder why, when I first introduced energy momentum tensors, we spent a lot of time talking about perfect fluids. Because in cosmology, we're modeling the universe as soup. soup, which is what state of matter?
Perfect fluid.
The soup state. Solids, liquids, gases, plasmas, soups. The soup state. Now, we're modeling the universe as a fluid. This is why you learned about energy momentum tensors for perfect fluids, because we're now going to apply them. Sorry it took so long. But here we go. So you know what the fiducial form of the energy momentum tensor for a perfect fluid looks like. It is the energy density plus the pressure times 2 factors of the 4 velocity of the fluid plus the pressure times the metric of the geometry. We are going to assume that we are at rest with respect to this fluid. And just because I got to get a card on the table, Avery is the lucky winner, loser, however you want to call it. Avery, what is the 4 velocity vector that we would use?
Gamma 0.
Exactly, 1, 0, 0, 0. And actually I should say it's, yeah. If you're at rest with respect to the overall fluid, then your 4 vector has no spatial motion. You don't have any spatial velocity. So the spatial parts are 0. But remember, this thing is restricted to be that, okay? So, all right. So we've got a particularly simple form of the 4 velocity that is an assumption that we're at rest with respect to the fluid. And then using that in this expression, we have the following matrix form. I don't even want to know.
It looks like poo.
I'm putting your card on top. I'm not even putting your card on top. I'm just going to call your name. Who said it?
Caleb said it. I said it.
Adria's in the deck twice, so I'm assuming by statistical odds, if I drew a random card, it would probably be her. So let's just assume Adria answers all questions and so forth and so on. Okay. So this is the form of our energy momentum tensor. Okay. We lose the pressure term because the pressure appears here, but it gets the 1, 1 contribution from here, but then we get the -1 contribution from the metric. Okay, so the pressure cancels out of this, and you're just left with the energy density. And then the spatial part, since this thing only has a term in the upper left, the spatial part is determined by the spatial parts of this thing. Now, I want to be careful because when you build the energy momentum tensor, you use the full metric. You don't just use the spatial metric. These are mu's and nu's. This is the full geometry. Okay? So when I write this, it is not the same as that. The difference is that Gij includes R squared. It includes, say it again? Well, eventually A squared, yeah. My comparison, though, is at this notation level. But anyway, okay? All right, here we go. So, on to Einstein's equations. And if we write them in trace reverse form, which we first did for the case of the Schwarzschild solution, but it's going to turn out to be useful here as well. Okay, we have an expression which looks like that. And now all we're going to do is we're going to take this metric, we're going to plug it in here. Now it appears in several places. It obviously appears in here through a bunch of derivatives and then quadratics in those derivatives and then also second derivatives. You could use Mathematica for it. Okay, it also appears here. And it also appears here because it's part of the energy momentum tensor. And it also appears here. So the metric is going to be in it's going to be in every term here. Okay? And then, of course, for the form of T mu nu and T, we would get that from our assumption of the perfect fluid energy momentum tensor. So I'm just going to jump to the chase. I'm not going to derive what these things look like. Most of it you would just get from Mathematica anyway. But if I think about the mu equals 0, nu equals 0 term, which I'll just call the 0, 0 term, then this ends up giving me an equation of the following form. And if at any point it's not clear what's a rho versus a p, let me know and I'll clarify. And then if I take two spatial terms, so generically ij, and this will include the case where they're the same, so you can do ii, but it's more general, we can do two different spatial terms. But these are only spatial, they're not space-time terms. Then we get an equation of the following form. And what I'm writing down now is in no way, shape, or form obvious, right? Because you would have to plug this into Mathematica, you'd have to get the Einstein, or the Ricci tensor, and then you'd have to get the form of the right-hand side by working with this in the metric. It's very, very non-trivial. Okay, but at the end of it, here are the time-time components of Einstein's equation in trace reverse form and the spatial-spatial components. We could write down a space-time component, like a 0i, but we're not going to need that now. And then what we can do is we can merge these two expressions because they both clearly involve a double dot over a. So we can merge them to get rid of that second derivative term. And in doing so, we get an expression of the following form. And sorry, that's a capital K there. Okay. Which is called and oh God, I spelled, this is, sorry, I got freaked out because I thought I spelled something horribly wrong and I haven't used this word yet. This is called the Friedmann equation. Okay. So the Friedmann equation is what we get when we take the Robertson-Walker metric and we plug it into Einstein's equations, assuming a perfect fluid source. This is a very useful equation. Solutions to this equation are called Friedmann, Robertson-Walker, or FRW cosmologies. So that's where the three names that I sort of said at the beginning of the lecture are finally getting into the story. Now is where we start getting into some interesting stuff. Okay? It all has to go by way of very dry mathematics, because if I just drew really cool pictures and said, oh, black hole, if you go in, you come out another universe, you'd all be like, right. But I think you underpin it with some solid math, and you're like, right. Okay? So we're going to talk about solutions to the Friedmann equation. We're going to talk about FRW cosmologies, and these are a very good first approximation to the behavior of our universe. But I got to introduce some new notation, obviously, because that's what it's all about. So I'm going to, instead of considering the quantity a dot over a, and remember, a depends on time, so the bottom is a function of time, and then clearly the top can be a function of time. And dot, of course, I haven't been using dot a lot, but dot is time derivative. It's the only derivative that matters because a only depends on time, so I have adopted a dot notation for my derivatives. I'm sorry I didn't say that earlier. The combination a dot over a is a quantity we call h of t, where this is what is known as the Hubble parameter. I heard that. And so did you.
Classes here and all the words that space things are named after, and then go.
I know. That's what's nice about talking about cosmology is like we will touch on ideas that you've all seen and heard before in various contexts. Okay. So in terms of the Hubble parameter, the Friedmann equation takes a very nice form. This equation we will make extensive use of throughout today and the next topic. Okay? But let's actually look at an implication of what is relevant here. So if I want to say, if I look out and see something and I ask, how fast is it moving? then what I'm asking is, what is the physical velocity of that object? Okay? The physical velocity of that object is defined in a very natural way as the time derivative of the physical distance of that object from me. So I look out, I see something, it's got a physical distance, and then how that distance is changing with time tells me about the physical velocity of that object. Now, the thing to realize is that if you have a physical length, you can write the physical length in terms of the coordinate length, which remember is a constant, by the scale factor. Okay? So to go from a coordinate length to the actual physical distance, you just use the scale factor. But of course, L coordinate is constant, so this time derivative actually only acts on A. So this expression just becomes A dot L coordinate. But I really don't like coordinate distances. They're not physical, so let's actually write this in terms of the physical distance. So the physical distance, well, the coordinate distance is the physical distance divided by A. Which is, of course, just HL physical. Now, you might not be impressed yet, but you're about to be. What this expression is telling us, that the physical velocity seen when I look out at something is proportional to the physical distance, is called Hubble's law. The importance of Hubble's law, which I'm going to illustrate, is that it tells us that the universe is expanding. And when I say that, I mean something very specific, which is often misunderstood when people think about the universe expanding. So I'm going to illustrate this with two pictures. So, in the first picture, I'm going to place an observer at the center dot. And in the second picture, I'll place the observer at the center dot. And all these observers are going to do is look at what's going on around them. Okay? Now, this is going to be an x-axis. And I'm just going to place this guy at x equals 0, and then just for simplicity, integer coordinate values. Right? Okay. So the first thing that I want to do is I want to come over here and I want to ask if these objects were the result of an explosion of matter. Okay? So you had all these things at one point and then they just went. Okay? In this story, what would you see? So this is explosive. Well, what you would see is that the objects over here would be moving away from you with whatever velocities they were imparted when the explosion happened. There's no reason for those velocities to be changing. And similarly, these would be moving in the opposite direction. And I don't have my vector hats on there, so Phys 1 TAs, you just have to suck it up. Actually, I do have vector hats over here. Look at that. I accidentally drew vector hats over my vectors. And here they're not vector hats. Anyway, it doesn't matter. Okay? Does that make sense? Like literally, if I took so I'm going to explode. I'm going to have 4 pool balls and explode. And that explosion is going to be, I'm going to throw 2 of them, and then a second later I'm going to throw the other 2. And I'm going to throw them all at the same velocity, or at the same speed. One that way, one that way. Okay, and when I look over, I see the one that's further from me moving at the speed, and then I see the one that's closer to me moving at the same speed. There's no reason for those speeds to change. Okay? That's what happens when things explode. Now, I want you to look at this picture, and I want you to consider not explosion, but expansion. That is, these things are sitting on the x-axis, and the x-axis is just growing. If I'm sitting here, and I look at this guy, and this guy happens to be moving at a velocity v naught to the right, I will see this guy actually moving faster. You're going to have to just take a minute to think about that. But in fact, this guy would be moving exactly twice as fast. Okay? I mean, think about it. If the x-axis doubles in size, then this distance has changed by a factor of 2. Okay? This distance has changed by a factor of 2. But this thing has only moved 1 unit, where this thing has had to move 2 units. So it's moving twice as fast. And similarly over here. So when things are expanding, the velocities you see when you look around are not at all like the velocities you see when you look around where you have an explosion. Now, which of these obeys Hubble's law? This does. Say it again?
You didn't even let us guess.
Which one of these obeys Hubble's law? This one. Which one does not?
The other.
That one. Okay. Let me make one more comment and the punchline, and then I'll let Avery ask a question. Here's the other really important and cool observation. If I'm standing right here and I look to the right, I see shit moving away from me. And if I look to the left, I see shit moving away from me. If I stand here,
Same thing. You get this one.
if I stand here,
Everything's moving away.
We see shit moving toward the,
yeah, I don't see the same thing depending on where I'm standing. Okay? I see different things if I'm here versus here versus here versus here versus here. Come back to this picture. If I'm standing right here, I see this stuff moving away from me, obeying Hubble's law. If I stand right here, I see the exact same thing. Expansion, this is where the space-time is expanding. Expansion allows for things to move apart, yet everybody sees the same thing. That's the homogeneity we said we observe in our universe. You don't get that from explosive growth. So the idea, the gist of this is when we say the universe is expanding, we're not talking about that we have space and shit's just flying apart. That's this picture. It's wrong. It's not what general relativity is telling us. General relativity is telling us that the actual space-time that everything is sitting in, that itself is expanding. And that is a fundamentally different behavior than this kind of explosive expansion.
So when you're talking about, like, if you placed yourself at x equals -2, and when you look around, everything looks the same as if you're at x equals 0.
Yes.
Doesn't that sort of imply a Newtonian addition of velocities based on the picture you drew? Because you're sitting at -2 and saying -1 or negative v naught is 1 less, so it looks like it's going 1 v the other way.
Yeah, that's actually perfectly reasonable. There's nothing that says these have to be relativistic velocities. I mean, we're talking about the behavior of a curved space, but the time evolution can be very slow. So it's perfectly legitimate to be working in a Newtonian limit. I don't even know if it's worrisome if these relative velocities are, well, yeah, I mean, actually, Yeah. So, yeah, I want to be careful because I'm not, okay, yeah. So, when you talk about velocity addition being different in special relativity versus Newtonian Galilean relativity, that's what you mean, but Galilean relativity, what you have in mind is, I look at an object, and then I ask, what would and the object, I see some velocity for the object, and then I say, okay, there's some person who's in motion relative to me looking at that same object. What velocity would they see? I'm one person looking at various objects and asking what are their velocities. But the formula that I'm getting is from general relativity, so it's clearly got special relativity built in. Okay? That being said, you could still be describing, stuff doesn't have to be super fast in general relativity just because the word relativity is in there. Okay? It cares way more about the curvature. Okay, so, home stretch. Okay, so we have Hubble's law. We have the Friedmann equation written in terms of the Hubble parameter. We've observed that the fact that our universe is described by Hubble's law indicates that space-time is expanding or space-time is changing and not this explosive interpretation. And now what I'm going to do is fill out the rest of the story for let's actually, gotta erase stuff. Let's actually finish solving Einstein's equation. So go ahead and ask your question, Gabriel.
So does this mean that something far enough away from you is moving away from you faster than the speed of light?
It can. It certainly can. Yeah. There's no problem with that.
And the way this goes to infinity, these things keep, space keeps expanding. So what happens to the molecules in your body?
Interesting question. Very interesting question. So when we say that space expands and that therefore objects move apart, we are only telling you this story in the context of gravity. There are other forces at play for the atoms and molecules, the protons and neutrons. And so normally what happens is the other forces like electromagnetism will keep things bound at a fixed size. So while the atoms in your body aren't going to stretch out because of the expansion of space-time, because there is another force holding them at a fixed distance, two things which are not connected through a force other than gravity, those two things will separate. Okay?
Is there a limit that the expansion of space can overcome the other forces?
If it was really fast, yeah, I mean, shit can happen. I mean, we're going to talk about a situation in the next lecture where we have a very rapid expansion of space, and it leads to a lot of really weird stuff. Not bodies being ripped apart per se, because you weren't around at that part of the history of the universe. But I'm glad you brought that up, because a lot of people think, oh, if space is expanding and everything's expanding, then you can't really tell. Like, you go to measure something, so you hold a ruler up, but the ruler's expanding, and the thing you're trying to measure is expanding, and so you just keep getting the same length, and you're like, WTF? What's that, Flournoy? Well, the ruler won't expand, because the ruler's length is set more by the electromagnetic attraction of the atoms it's made of. Okay, I gotta shut it. I gotta keep going. All right. Okay, so I'm now going to dump a couple of ideas on you. These are relevant for solving this to its final form. But this is where we actually have to start asking ourselves what's out there, what's in the universe. Okay? So we have in this expression, or in the form where we talk about it in terms of A dot over A, and I'll sometimes move back and forth between the two. We need to know this thing. We need to know the energy density rho, because it appears in the equation, and we need to know the spatial curvature kappa. We can measure h, and I'll talk about how you measure things in the next lecture. So we can actually measure the physical value of h. We can measure k. These are things we can actually get from observing our universe. This thing is a little more tricky. Figuring out what the energy density of our universe is more subtle. And it actually turns out it gets a couple of contributions, which we're going to go over now. So first of all, Since A depends on T, and rho depends on T, we could take this and ask, how does rho depend on A? Okay, if they both vary with time, then you can take one of them, solve it for T, and then plug it into the other one. And then it turns out to be very useful to consider, how does the energy density change with the size, the scale factor A? That behavior is going to play a very important role in identifying what is and isn't important. So let us quickly consider the conservation of energy momentum, which in general relativity is expressed that the covariant derivative of the energy momentum dual tensor is 0. And if I take this and I use a factor of the metric to lower that mu index, then this is just going to become del mu T mu alpha equals 0. And then if I plug in the energy momentum tensor there, and I consider the component of this equation, this has only got one index, alpha. If I consider the alpha equals 0, the time-like component of it, then I get an equation of the following form. Okay? Again, that's not trivial or obvious at all, but that's what you'll get if you actually plug in the energy momentum tensor with the covariant derivative. And remember, the covariant derivative is going to be nasty, because you got to build it with the Christoffel symbols that are derived from this metric. So there's a lot of mathematical love in that. Okay? But we can take this and actually get something useful out of it. So what I'm going to do is I'm going to assume that my perfect fluid obeys an equation of state of this form. That is, there is a relation between the pressure and the energy density, and I'm just going to assume a linear relationship where that factor omega is just a constant. What's nice about this is that by picking different values of omega, we can talk about different forms of energy momentum, different forms of perfect fluid. So we can talk about dust, we can talk about radiation, we can talk about vacuum, just by picking different values of W. Okay, and I'll go over those examples in a minute. But if I take this and I plug it in right there, then that obviously just becomes rho plus rho, or omega rho. And then this simplifies to the following form. And then we can do a quick solve of this. Move one to the other side, move the rho underneath. Is there a minus there? Yes, there is. Okay? Which, integrating both sides, gives me that. This is just a constant. Plus a constant, but we're not going to worry about that. Okay? And then this has the solution. Remember, if I have a constant times a natural log, I can take this whole thing and put it as an exponent over here. And then I've got a log of something equals a log of something, so those two things are equal. So at the end of the day, this tells me that rho is a to the minus 3, 1 plus w. Remember I said it would be good to know how the energy density varies with the scale factor A. Well, there you go. Now what's amazing is that that's actually an intuitive result. If we consider various cases, it's not intuitive right now, but considering various cases, you're going to go, oh yeah, that totally makes sense. So let's actually think about it. So let's start with the case of matter. There we go. Or dust. So we're thinking of a dust energy momentum tensor. And one of the key features about dust is that it's pressureless. So the only contribution to the energy momentum tensor is just the energy density of the fact that you have particles in space, but they're not really banging into each other, causing a pressure. Okay. So if the pressure is 0, what's W? It's 0. Okay? So this is telling me that W is 0. All right? And if W is 0, then my solution is telling me that rho is a to the minus 3. Now let's think about that for a moment. The energy density of dust, if A grows, gets smaller by A to the minus 3. That's just saying it's as the volume gets bigger, the energy density gets smaller. You know, you think of density as energy over volume. Well, volume is A cubed. It's in the denominator. So as the volume grows, the energy density just gets smaller. That's intuitive. Okay? Somewhat intuitive. If I have a bunch of stuff in a box and I say the box grows, how does the density of stuff vary? It varies with 1 over the volume of the box. Okay? But it gets gooder. Shut up. You come and teach the class if you want to correct my grammar. Taking it back. If we have radiation, which is code for highly relativistic matter, so we could talk about stuff which is just moving like a bat out of hell, close to the speed of light, or we could just talk about photons, then we have that the pressure of radiation is 1/3 the energy density of radiation, which of course is telling us that W is 1/3. This is not obvious, okay? But take it as a given, then what we find is that rho is A to the minus 4. Okay? Which is intuitive, right?
Yes, absolutely.
Do you know what English?
It means it feels right. No, I'm kidding. You're gonna go, oh yeah, that makes sense. Okay, after I explain it. So, but when I say intuitive, sometimes you have to have an explanation. So what is happening here? Okay, so think of it like light. So I have these little photons, in a box. As I make the box bigger, the density of those photons decreases with a factor of A to the minus 3. But photons do something else, because if they're moving in a direction and you take that space and you expand it, they get redshifted, which also decreases their energy. But it's only in the direction of their motion. So that gives you an extra factor of 1 over A. So you get the volume dilution, the A to the minus 3, but then you get redshifting. Okay? So we get this A to the minus 4 scaling. If we have a vacuum, and you worked with this energy momentum tensor in your homework, then the pressure of vacuum is exactly minus the energy density of vacuum, which means that W is -1. So if we have a vacuum, then it actually does not depend on the scale factor. It's constant even if the universe changes its size. But vacuum is weird. Like, vacuum is not associated with the size of something. It's just this energy density intrinsic to the space-time itself. So if the space-time grows, that energy density doesn't change. It's a weird property of the vacuum. It's also the same as, when you were doing the homework and you said, what does the vacuum look like? What does the energy momentum tensor of the vacuum look like if you boost yourself? It doesn't change. You can't move relative to the vacuum. You can move relative to a fluid of stuff, but you can't move relative to the vacuum. Ask your question.
Wait, so if the energy density is the same as it's increasing, where does that stuff come from? Where's the energy? It's just there.
It's just there.
Okay.
Okay, I have a back page of notes, but I've already kept you longer than I should, so we will have to get to the Big Bang at the beginning of the next lecture. And I'm hoping to get through everything in the next lecture, because it is the last one of the semester, and we still have quite a few things to cover. But When we come back, we're going to start here, and we're then going to turn this into a question of, depending on which of these contributes to the energy of the universe, how does the universe behave with time? And then, of course, that's where we're going to uncover the fact that at t equals 0, the universe had 0 size. Right? Hence the Big Bang. We'll do that at the beginning on Thursday.